Ship 36 has fallen, its explosion tearing through Massey and halting progress in an instant. Images of the aftermath now emerge, offering a clearer view of the damage and the challenge ahead. But the question is no longer just went wrong, it is how SpaceX moves forward. What is the state of Massey, and what must be done to recover and resume testing? The Ship 36 incident remains a major shock for many, marking the first large-scale explosion we have seen at Starbase in quite some time. Following our previous update, we have now received a wave of new imagery that offers a more comprehensive view of the situation at the Massey Test Site. Thankfully, it appears that all immediate hazards have been mitigated. The site is now considered safe for workers and inspectors to enter. However, despite this positive step forward, the extent of the damage to several critical systems is unmistakably severe. To start, the test stand itself is in terrible condition. In one of the latest video captures, the damage is clearly visible. All signs indicate that the structure is beyond repair and will need to be entirely replaced. Just beside it, the Ship QD system also appears heavily exposed and stripped down, suggesting that it too may require major refurbishment or complete replacement. Moving outwards from the stand, additional damage becomes evident. A scorched horizontal tank can be seen at the far end near the test structure. Meanwhile, the steel support frames that run alongside the fuel lines have sustained visible harm. Not far from that area, a set of small tanks and a storage shed also show signs of being burned. Fortunately, there is no evidence of secondary explosions, and the nearby main fuel tanks seem to have remained intact. Debris is still scattered throughout the test site. One particularly large piece of wreckage is noticeable on the far side of the test stand, near the facility's drainage channel. This object could very well be a fragment from Ship 36 itself. In addition, the drainage system in that area shows signs of a recent fire alongside the accumulated debris. While it is unclear whether this was caused directly by the explosion or by routine testing residue over time, the system will clearly require a thorough cleaning. The effects of the blast also appear to have reached several adjacent systems. The side of the facility containing the test stand suffered the worst of it, with noticeable impact extending toward the office area and even reaching the vicinity of Test Tank 17's cage. That said, these zones are farther from the explosion site and seem to have sustained only minor damage. On the opposite side of the facility, which houses a large number of horizontal fuel tanks, the systems appear to have been spared entirely and remain in good condition. Cleanup operations have already begun. A crane was recently brought into the Massey area and crews have started clearing debris. This first phase of recovery will create space for a more extensive refurbishment effort in the weeks ahead. Altogether, the situation has stabilized. While the damage is substantial, SpaceX is clearly moving quickly to assess, clean, and begin the process of rebuilding the Massey Test Site. The next phase in the aftermath of the Ship 36 incident will focus on cleanup, refurbishment, and finding workable solutions to resume operations. However, one major question now looms: what will SpaceX do about the critical systems that were damaged or destroyed during the explosion? These include the test stand, the ship quick disconnect, and the surrounding fuel pipe network. Let us start with the fuel pipeline systems. These lines are essential for delivering cryogenic fuel to the vehicle during tests, and after the recent explosion, a full rebuild will likely be necessary. Fortunately, SpaceX has considerable experience laying down such infrastructure, and based on previous repair timelines, this could potentially be completed within a few weeks if prioritized. Next, we have the test stand. It is obvious from recent imagery that the stand is beyond repair and will need to be replaced entirely. The new stand does not need to replicate the exact design of the previous one, but it must integrate with the rest of the test system and support the same operational requirements. Constructing a new one from scratch may take time, but some believe that SpaceX could accelerate the process by repurposing existing hardware. One suggestion is to temporarily relocate a test stand from Megabay 2 for use at Massey, though doing so might create bottlenecks in Megabay's ongoing operations. As for the Ship QD system, there are rumors that SpaceX maintains at least one backup. If true, this could allow for a faster recovery. However, using this spare may deplete critical resources needed for other areas of Starbase and might disrupt work in progress on the next generation vehicles. The underlying strategy in all of this revolves around one key choice. Should SpaceX simply rebuild the damaged infrastructure to support the current Starship versions, or should it take this opportunity to begin transitioning to the newer version known as Starship V3? At first glance, rebuilding the old test systems seems logical. It'd allow SpaceX to continue testing and launching the remaining V2 prototypes, which include Booster 15, 16, and 17, along with Ship 37, 38, and 38. These vehicles are still viable and waiting for their turn in the launch queue. Rebuilding the test infrastructure for these existing vehicles would seem to offer the quickest path back to flight, but that solution may only be a temporary fix. When we take a closer look at the long-term strategy, several issues emerge. The number of remaining V2 prototypes is small. Rebuilding an entire test system for just a few remaining flights may not be the most efficient use of resources. Additionally, the V2 version of Starship has shown more issues over time, especially when compared to earlier flight history. Recent failures and the Ship 36 explosion further reinforce this pattern. Moreover, hardware constraints could present additional complications. The Ship QD system appears to be based on older designs, possibly repurposed from the suborbital testing days. That makes backups limited, and using the one remaining unit could jeopardize progress in Mega Bay 2 or other facilities. This brings us to a bold but promising option: building a brand new test infrastructure specifically tailored to support Starship V3. Yes, making this shift would mean skipping the few remaining V2 vehicles, which could be seen as wasteful. And yes, building an entirely new test stand would likely require more time, pushing the next flight beyond July. But in return, SpaceX would gain a robust system designed to support the next chapter of Starship development. Starship V3 promises a major leap forward. This version includes a wide range of improvements across systems. The upgraded Raptor 3 engines, for example, are expected to offer significantly higher thrust while being simpler and more reliable. Fuel tanks, plumbing, hot staging mechanisms, and overall structure are also set to undergo major upgrades. These changes aim to increase performance, enhance safety, and reduce complexity across the board. Starship V3 will also be larger and more capable, making it a more suitable platform for critical missions such as in-space refueling, lunar landings, and even crewed Mars missions. In that sense, building a dedicated test stand for V3 is an investment that will support the program for many years to come. Progress on V3 has already begun. B-18, the first V3 prototype, is currently being stacked inside Mega Bay. Meanwhile, S-39 is expected to be the first V3 ship, and it is nearly ready to begin stacking now that S-36's loss has opened up space in the bay. Even if the remaining V2 prototypes are not flown, they may still serve a purpose. SpaceX could salvage useful parts, recycle sections for structural testing, or even modify them by cutting and extending segments, as the diameter between versions remains consistent. In the end, the decision will rest with SpaceX. Will they rebuild the old system to get V2 flying again quickly, or will they take the longer route and prepare for V3's debut? What do you think? Reply with 2 if you support rebuilding the V2 test system, or 3 if you believe SpaceX should move forward with V3. Then, don't forget to like the video and subscribe to our channel to continue following the exciting development journey of Starship. No matter which option SpaceX chooses, one thing is certain: the company will do everything it can to bring Starship back online as quickly as possible. That sense of urgency has defined SpaceX's entire approach to the Starship program this year. Although recent events have put key milestones just out of reach, such as achieving back-to-back monthly launches or breaking the turnaround speed record, the broader mission remains the same. SpaceX is still aiming to set a new high for the number of Starship flights within a single year. If the company manages to repair the Massey Test Site in July and conduct a launch in August, it'll mark the 4th Starship flight of 2025. This would equal last year's total and leave several more months for additional missions. Achieving even just one more successful launch by the end of the year would break the existing record and set a new milestone in the Starship program. But it is not just about the number of launches. Returning to flight quickly gives SpaceX more chances to complete a growing list of mission objectives. Several critical goals have still not been fully achieved in the first half of 2025. These include deploying payloads in orbit, successfully reigniting engines in space, performing controlled re-entries, and landing both stages intact. Completing these steps will be essential before moving on to even more ambitious plans. Looking ahead, Flight 10 could serve as the mission to close out these incomplete tasks. If successful, it would pave the way for even more advanced tests in Flights 11 or 12. One of the biggest potential milestones could be attempting to catch the returning upper stage using Mechazilla's tower arms. That kind of recovery will demand a very high level of precision and reliability, standards that can only be met after nailing the fundamentals in earlier flights. Thanks to the progress made this year on infrastructure and hardware, 2026 already looks promising. Musk has emphasized the importance of developing the orbital refueling system, which will be a central focus moving forward. However, that system requires Starship to demonstrate consistent, repeatable performance. That means the remaining months of this year are crucial for validating Starship's core capabilities. SpaceX also has regulatory momentum behind it. The FAA has approved up to 25 Starship launches for 2026, giving the company a solid window to increase cadence and push the platform toward uncrewed demo missions to the Moon and eventually Mars. Although the recent setback at Massey was a serious one, it does not necessarily spell disaster. In fact, the incident may become a catalyst for innovation. The damage has highlighted weak points in the testing infrastructure, but this could inspire SpaceX to apply better, more robust solutions that will strengthen the overall roadmap for Starship. Once the team identifies a clear solution, we can expect to see them move quickly to implement it. The race to return Starship to flight is already underway, and the second half of 2025 could become one of the most transformative periods yet in the program's history. So, stay tuned, because Starship's most exciting milestones may still be just around the corner. Time to return to the spotlight. What once seemed like an ambitious timeline for Starship is now taking shape as activity ramps up once again at Starbase. Could the next launch happen sooner than expected? In other news, SpaceX has completed another successful rideshare mission, but not without complications, as one of the onboard payloads has reportedly run into trouble. And over in Japan, the mystery behind the failure of the Resilience lunar lander has finally been solved. The S-36 incident at the Massey Test Site has significantly slowed progress for SpaceX's Starship program. If this failure had not occurred, we might already be counting down to Flight 10. However, the damage has already been done, and now all attention is focused on cleanup, evaluation, and a carefully executed recovery process. SpaceX must move forward decisively to bring Starship operations back on track. Fortunately, recovery efforts began almost immediately. On the afternoon of June 20th, just days after the explosion, the first crane was spotted moving into position at the Massey area. Simple debris cleanup started soon after, which was an encouraging sign that the site was once again safe for human access. This initial progress set the stage for more comprehensive repairs and investigation. By June 21st, operations escalated. The crane was seen attempting to lift large fragments of debris. Some wreckage was so heavy that it had to be dragged rather than lifted completely off the ground. Then, on the 24th, during efforts to remove a particularly massive piece of wreckage, the crane reportedly toppled. Fortunately, the situation did not appear to result in major injury or significant delay. The large debris was eventually either placed onto transport vehicles or set aside in designated areas for later removal. Post-incident imagery of the Massey Test Site reveals significant damage. The test stand, nearby tanks, and surrounding infrastructure were all affected by the explosion. As such, the cleanup is expected to take several more days, possibly even weeks. Following the removal of debris, SpaceX will need to refurbish or replace critical systems. These include the tank farm, fueling infrastructure, test stand components, and the ship quick disconnect arm. Only after those systems are restored can SpaceX resume cryogenic and static fire testing at Massey. Despite these obstacles, SpaceX is pushing forward. Across other parts of Starbase, notable progress continues. On the 21st, 2 MOVAC tanks were transported to the launch site. Then, on the 24th, an impressive convoy of nearly 20 water trucks arrived. Although it is still unclear whether these assets are intended for Launch Pad A or Pad B, the movement of this equipment strongly suggests that Starbase is gearing up for further testing or pad readiness procedures. At the production site, developments are also underway. The hot staging ring, which had been moved from Megabay back to Star Factory for adjustments, was returned to Megabay shortly afterward. This indicates that it may soon be installed onto B-16, which is being prepared for Flight 10. B-16 remains on schedule, so ultimately the timing of the next launch will be determined by the status and readiness of the next Starship vehicle. With S-36 now destroyed, S-37 is the most likely candidate to take its place on Flight 10. S-37 completed assembly earlier this year and successfully passed 2 cryogenic tests by the end of May. This suggests that it is largely ready for the next phase of qualification. However, one major hurdle remains. The vehicle has not yet undergone its static fire test. The usual location for this test would be the Massey Test Site, but that facility is currently inoperable due to the recent incident. Although Launchpad A has all the necessary systems for testing, it appears that its orbital launch mount is not a combination of the current iteration of the ship prototype. As for Launchpad B, construction is still ongoing. The manifold installation is not yet complete, and after that step, the platform will need to undergo individual system tests followed by full-scale integration checks. This creates a serious bottleneck in the testing timeline. Unless an alternative solution is found or Massey is rapidly brought back online, the static fire test for Ship 37 could be delayed by weeks or more. One bold idea that has emerged is the possibility of skipping the static fire test entirely. If SpaceX chooses this path, they could begin final checks and installations immediately. This would include integrating the flight termination system, the payload adapter, and any mission-specific equipment. Once these steps are complete, S-37 could be stacked on top of B-16 and moved to the launch site. A full wet dress rehearsal with the stacked vehicle would likely follow, testing systems under realistic pre-launch conditions. However, this approach would be highly controversial. Static fire testing plays a critical role in validating a vehicle's flight readiness. It allows engineers to inspect engine behavior, fuel tank integrity, COPV performance, avionics, and other key subsystems under real stress conditions. Skipping this step could leave undetected issues lurking inside the hardware, especially given Starship's history. COPVs, in particular, are now under intense scrutiny. The explosion of S-36 has been traced back to this component. Failing to verify their performance through a static fire test could increase the risk of another catastrophic failure. And while skipping static fire testing is possible in theory, since SpaceX has done this before with Falcon 9, it is worth noting that Falcon 9 is a mature vehicle with hundreds of successful missions under its belt. It has earned that flexibility through consistent performance. Starship, by contrast, is still in development. Every recent flight has encountered significant issues. Even B-14, which had already flown once, had to undergo full testing again before being cleared for its second flight. This demonstrates the level of caution still necessary when working with such a massive and complex vehicle. Given all this, SpaceX faces a critical decision in the coming days. If the company is confident in its systems and believes that the lessons learned from past flights, including the S-36 incident, have been fully addressed, then a bold move toward launch without a static fire might be feasible. However, if mission success is the priority, and it should be, then a more methodical approach would be preferable. The return to launch operations will depend on how thoroughly SpaceX can resolve the issues identified in recent months. The company will need to conduct deep inspections, reinforce quality control, and ensure that all subsystems, from engines to fuel tanks to COPVs, are functioning as intended. These steps will form the foundation for a truly successful mission, which would break the streak of troubled flights seen in the first half of 2025. Still, the sense of urgency remains. The public is eager to see Starship fly again. With the growing pace of global competition, including rapid advances from China and other private players like Honda and Blue Origin, SpaceX needs to demonstrate progress and regain momentum. At the same time, careful preparation now will pay dividends later. A clean, successful flight would boost investor confidence, reaffirm NASA partnerships, and accelerate timelines for key missions like Artemis, Starlink deployment, and Mars colonization. In the end, SpaceX must balance ambition with caution. That balance will determine whether Flight 10 becomes a breakthrough moment or another setback. If you agree that preparation is the key to progress, type "Yes, Kevin" in the comment section down below. Then, like the video and subscribe to our channel to stay updated on Starship's journey and everything happening at SpaceX. Anyways, let's move on to an update regarding the Falcon 9 Transporter 14 mission and its payloads. At exactly 5:25 p.m. Eastern on June 23rd, SpaceX launched a Falcon 9 rocket from Space Launch Complex 4E in California. This mission, known as Transporter 14, is part of SpaceX's well-established rideshare program designed to carry a wide array of small payloads into orbit for various clients around the world. In orbit, the second stage of Falcon 9 executed its deployment sequence, releasing each payload one by one into their respective target orbits. By all initial reports, the mission was largely successful, once again proving the efficiency and reliability of SpaceX's rideshare program. Despite the success of the launch itself, not every payload performed as expected after deployment. One of the most notable issues involved the re-entry capsule deployed by the exploration company. This payload, ironically known as Mission Possible, was intended to demonstrate the company's ability to return cargo safely from space to Earth. The capsule, which weighed 1.6 tons and carried around 300 kilograms of cargo for various customers, was the final payload deployed on the mission. It separated from the second stage approximately 2 hours and 45 minutes into the flight. The capsule was designed to re-enter Earth's atmosphere and splash down in the North Pacific Ocean, where it would then be recovered. According to the exploration company, the initial post-separation phase went smoothly. The capsule powered up as expected, stabilized itself, and began executing its planned maneuvers. However, shortly after splashdown, communication with the spacecraft was lost. The company issued a statement explaining, "It encountered an issue afterwards based on our current best knowledge, and we lost communication a few minutes before splashdown. We're still investigating the root causes and will share more information soon." The company's public apology to its clients indicates that the capsule and its payloads are presumed lost. They stated, "We sincerely apologize to all our clients who entrusted us with their payloads. While disappointing, this setback highlights the inherent challenges of spaceflight, particularly in the field of orbital re-entry and recovery. Even so, it is important to remember that setbacks like these are not uncommon in the aerospace industry. Every test flight carries risk, and every challenge presents an opportunity to learn and improve. The exploration company remains among a growing number of private organizations working toward making space more accessible and versatile, and this experience will likely guide refinements in future capsule designs and recovery operations. In the larger picture, the mission once again demonstrates SpaceX's critical role in advancing access to space. Through its rideshare program, companies around the globe have an affordable and dependable means to get their payloads into orbit. While not every mission goes exactly as planned, the path forward is shaped by persistence, adaptation, and collaboration. As the space industry continues to expand, we can expect more of these companies to push boundaries, attempt bold new missions, and grow stronger from their experiences. The dream of reaching space is not easy, but it is clearly within reach for those who are willing to keep going. Now, let us turn our attention to an update on the cause behind the failure of Japan's Resilience lunar lander. Weeks after its failed lunar landing, Japanese company iSpace has released findings on what caused Resilience to crash. The issue stemmed from a malfunction in the lander's laser rangefinder, which failed to provide valid altitude data during descent. As a result, the lander couldn't slow down properly and impacted the surface near Mare Frigoris on June 5th. This marks iSpace's second failed lunar attempt, following the loss of Hakuto R in 2023. The exact cause of the LRF failure remains unconfirmed, but iSpace has outlined 4 likely contributors: unusual surface reflectivity, poor laser angle, weak signal strength, and possibly system degradation due to radiation or miscalculated descent dynamics. In response, iSpace is strengthening testing protocols and upgrading landing hardware. Its upcoming missions, Mission 3 and 4, will debut the new Apex 1.0 lander, equipped with improved vision-based landing systems to replace or support the traditional LRF. Despite the setbacks, iSpace remains committed to advancing Japan's role in lunar exploration and supporting humanity's long-term presence on the moon. Unbelievable scenes. SpaceX has just experienced a major setback on the road to its next Starship flight, and the scale of the damage is only now coming into view. This unexpected and unprecedented failure could have far-reaching effects, potentially casting a shadow over the entire Starship program for the remainder of the year. Some are even beginning to ask, could this mean no more Starship launches in 2025? Just how serious is the fallout from the loss of Ship 36? Is it truly possible that we might not see another launch this year? And most importantly, can SpaceX recover and return to flight in time? Indeed, unbelievable scenes have unfolded. SpaceX has just suffered a major blow on its path to the next Starship launch, and the true extent of the damage is now only coming into focus. The incident occurred during a 6-engine static fire test involving Ship 36 at the Massey Test Facility. What was expected to be a routine pre-flight check turned into a catastrophic explosion that completely destroyed the vehicle and may have severely damaged the surrounding test infrastructure. Even longtime followers of the program were caught off guard by the scale and suddenness of the failure. While SpaceX has faced setbacks before, from hard landings to in-flight anomalies, none have matched this moment in terms of shock and scope. This was not just a failed ignition, it was a violent eruption that engulfed the test site in flames, sending a fireball into the night sky and igniting immediate concerns for the Starship schedule ahead. The explosion happened just after 11 p.m. Central. Leading up to the blast, observers noticed unusual venting patterns, possibly pointing to fueling or pressurization issues. Then, without warning, Ship 36 exploded and the resulting blaze burned for several minutes. Emergency teams were dispatched quickly to contain the fire and secure the area. SpaceX has since confirmed the anomaly, noting that no one was injured and that there were no hazards beyond the site. Local officials were also notified and remain in coordination with SpaceX personnel. However, the company has yet to release a cause for the failure. Current speculation suggests a possible methane or oxygen leak that may have ignited due to heat, pressure, or a faulty connection. Given the volatile nature of Starship's propellants, even a small flaw in a valve or seal can trigger catastrophic results. The destruction of Ship 36 is a major blow to the flight timeline, as 36 had been assigned to carry out the highly anticipated Flight 10. With it now lost, SpaceX must pivot quickly, most likely turning to Ship 37 as a replacement. But S-37 has yet to complete critical tests, and with Massey damaged, it is unclear when full-scale testing can resume. That is why some are asking the difficult question, could this ground the Starship program for the rest of the year? While that may sound extreme, the challenges ahead are real. First, SpaceX must investigate the root cause of the explosion, a process that requires extensive analysis and engineering review. Second, they will need to repair or rebuild any affected systems at Massey, which could take weeks. And finally, they must prepare and qualify an entirely new vehicle for flight. That means more tanking tests, engine verifications, and another static fire, all before even thinking about launch. This setback comes just days after the FAA officially listed June 29th and the 30th as target windows for Flight 10. A launch on either of those dates would have broken SpaceX's record for the fastest turnaround between Starship missions, clocking in at just 33 or 34 days since Flight 9. That milestone now appears out of reach. B-16 is still progressing on schedule. Its hot staging ring has been installed and flight hardware preparations are nearly complete. But without a validated ship to pair it with, it too must wait. In the short term, this incident will almost certainly cause a delay of at least 1 to 2 months, possibly longer. That depends on how fast the Massey site can be brought back online and how quickly S-37 can be verified for flight. In the worst-case scenario, if deeper issues emerge or repairs take longer than expected, the next Starship launch could be pushed into late 2025. Still, if any company can turn a failure into progress, it is SpaceX. Time and again, they have proven their ability to adapt, iterate, and return stronger. They learn quickly from setbacks, and the rapid pace of development in the Starship program has always reflected a willingness to embrace risk in pursuit of breakthrough capabilities. So while the road ahead has become more uncertain, it is far too early to count Starship out. SpaceX has overcome greater challenges before, and there is every reason to believe they will do so again. What do you think? Can SpaceX recover in time? Will Flight 10 still lift off this year? Let us know in the comments. And also, reply keep going to show your support, and don't forget to like the video and subscribe so you never miss out on a moment of Starship's bold journey to the stars. Now, let us take a closer look at the updated cause of this dramatic incident involving Ship 36. When the explosion first occurred, many speculated that the root of the problem was a leak either in the fuel tank or one of the engines. That was my initial theory as well. However, as engineers and industry analysts began to dig deeper, a clearer picture started to emerge, one that points to a very specific and concerning hardware failure. One of the most valuable summaries of this technical analysis comes from Ryan Hansen, who compiled insights from various aerospace engineers. Before diving into the details, I would like to express my gratitude to Ryan Hansen and his team for their excellent breakdown of the issue. Their work has helped bring clarity to what might otherwise remain a mystery. I encourage everyone watching to follow Ryan's X page and subscribe to his YouTube channel to support further quality content and technical insights. According to the engineering analysis, the problem originated in the composite overwrapped pressure vessel, located within the payload bay of the ship. The COPV system is typically used to store high-pressure gases, in this case nitrogen, and it is situated around the fuel lines of the header tank inside the payload section. Due to a failure that has yet to be fully confirmed, the nitrogen COPV appears to have ruptured. This rupture created a sudden and violent release of pressure, blowing open a section of the ship's windward side, which is the side covered by heat shield tiles. The explosion also appears to have ruptured nearby fuel lines connected to the header tank. With the fuel lines compromised, propellants likely began to leak uncontrollably. The released propellant rapidly filled the payload bay area, and as pressure mounted, the forward dome of the fuel tank sustained damage. The growing internal damage and structural failure ultimately caused the leaked fuel to ignite, triggering the massive fireball and explosion witnessed during the test. This chain of events aligns with what we observed: a sudden, intense explosion during the static fire preparation phase, not during engine ignition. Only a catastrophic internal failure like this could explain the rapid and total destruction of Ship 36. These early suspicions were later confirmed by official statements from both Musk and SpaceX. Initially, Musk referred to the damage as just a scratch, but he later provided more technical insight. In a post on X, he wrote, "Preliminary data suggests that a nitrogen COPV in the payload bay failed below its proof pressure. If further investigation confirms this, it would be the first failure of this design." Following that, SpaceX released its own official statement. They explained that a sudden energetic event occurred during cryogenic propellant loading and that the initial cause appears to be a failure in the pressurized tank system. This tank again refers to the COPV used for storing nitrogen inside Starship's nose cone. SpaceX also clarified that there is no design overlap between this Starship COPV and those used in Falcon rockets. The confirmation from both Musk and SpaceX validates the original analysis made by the engineers. Furthermore, some observers noted unusual activity in the days leading up to the explosion. SpaceX crews were seen working extensively on Ship 36's payload section after its single-engine static fire test on June 16th. This detail supports the theory that a known issue may have existed within the COPV or related systems before the catastrophic failure. Clearly, the payload section, especially with the addition of moving parts like the payload door, complex pipework, and high-pressure storage, is becoming one of the most technically sensitive areas of the Starship architecture. Now that we better understand what happened, the next big question is whether SpaceX will still be able to launch another flight this year. Many believe that after such a severe and unexpected problem, the odds of another Starship flight happening in 2025 are significantly reduced. It's worth noting that Ship 36 is the first full-scale flight prototype to ever be destroyed during ground testing. This is an unprecedented event. Musk himself acknowledged that this failure mode had never occurred before, and with no historical reference, the time required to resolve the issue remains unknown. Another concern is the damage to the test stand at Massey, which could take weeks or even months to repair. If future ships cannot be tested on Pad B in the meantime, then progress is stalled until those facilities are restored. Additionally, while the FAA may not require a full mishap investigation, since the test did not involve a licensed launch, local environmental agencies might still become involved. If that happens, SpaceX will need to comply with their assessments before continuing test operations. However, I remain cautiously optimistic that we will still see another flight this year. There are a few key reasons for this. First, as mentioned earlier, the FAA does not require a mishap investigation because the explosion occurred during a ground test, which is not covered under the agency's launch license. That means SpaceX can conduct its own internal investigation and move forward without formal federal delays. Secondly, SpaceX has stated that there were no injuries or hazards to the public. This significantly reduces the likelihood of prolonged regulatory involvement. And let us not forget that Starbase itself operates like a company-run city. As long long as the impact remains within its boundaries, SpaceX will retain some flexibility in managing the situation. Lastly, we are still only in the month of June. There are 6 months remaining in the year, and that gives SpaceX a reasonable window to investigate, repair, retest, and potentially conduct at least one more launch. Of course, we would love to see more than one, but even a single additional flight would mark a successful rebound. In conclusion, this was a deeply unfortunate and unexpected incident for SpaceX. The failure of the COPV system inside Ship 36's payload bay has introduced new technical challenges and delayed immediate flight plans. It also highlights that despite the progress made, Starship still has many systems that need refinement and stress testing. But let us also remember that the purpose of testing is to find problems before they cause failures in space. Musk himself said room for improvement, as failure is not just acceptable in early development, it is essential. Each mistake is a lesson, each setback an opportunity to improve. So let us continue supporting SpaceX during this critical moment. If you believe they can solve this issue and launch again before the year ends, drop a yes in the comment section down below. And no matter what, reply, "Let's come back soon," to show your support for the engineers working tirelessly to build the future of spaceflight. SpaceX employees have just revealed more details about the issues that led to the failure of Ship 36, and there are several key points that are worth discussing. In other news, ULA's Atlas V has successfully completed its second mission for Amazon's Project Kuiper. Meanwhile, China has carried out a new test of its well-known Zhuque-3 rocket engine, which has often been compared to other leading designs in the industry. The Ship 36 incident continues to capture widespread attention. The more we uncover about what happened, the more it reveals about deeper issues, not only with this particular vehicle, but also with the Starship program as a whole. Recently, several new revelations have come to light, this time from a former SpaceX employee named Morgan Wyatt Kahn. According to Morgan, many of the issues leading up to the Ship 36 explosion may be tied not only to technical challenges, but also to poor workmanship and substandard procedures at the Starbase facility. One of the most discussed components recently is the Composite Overwrapped Pressure Vessel, or COPV. SpaceX and Elon Musk have both identified a failure in this system as the likely cause of the explosion. Independent analysts have also pointed to a COPV rupture, which likely compromised the structural integrity of the ship, severed fuel lines, and ultimately triggered the devastating explosion. However, the question still stands: why is the COPV failing in the first place? While previous discussions have explored complex technical issues and broader design challenges, Morgan's account offers a new and concerning angle. He claimed that during what he called the tent era at Starbase, some workers would routinely slam COPV bottles into the retrofitted brackets in the payload section. According to Morgan, he was responsible for handling issue tickets related to these actions and was forced to assess the resulting damage. This practice is especially dangerous. Even when COPVs are not pressurized, rough handling can easily cause microcracks or internal damage. Any hidden defect could result in catastrophic failure once the vessel is pressurized or exposed to cryogenic temperatures. According to Morgan, the damage was so severe that at one point, the entire program had to halt operations while they waited for new COPVs to arrive. And unfortunately, the careless treatment of these components did not end with delivery. Morgan went on to describe poor installation practices as well. He stated that COPV distribution pipes were often loosely tightened, lacked proper sealing, and in some cases were held in place with cross-threaded bolts of the wrong size. These oversights suggest not just a lapse in quality control, but also a lack of proper training or experience among workers involved in these crucial tasks. He also speculated about the exact failure that might have occurred with Ship 36. In his view, it is possible that the COPV plumbing was never properly sealed. This could mean that the hardware was not fully integrated or that seals were broken, missing, or incorrectly installed. Loose or missing components could also have played a role. Another question that has come up is why the problem did not appear earlier during cryogenic testing or the single-engine static fire test. Morgan said that stress and strain limiting factors could be chokeholding the stack up on hardware. He also pointed out that the stainless steel used in Starship construction is particularly vulnerable to thermal shock, which could further contribute to sudden failures. When subjected to extreme temperature changes, stainless steel can contract rapidly, which may even lead to damage to the heat shield tiles. But technical challenges aside, perhaps the most concerning point Morgan raised is how management at Starbase has been handling these issues. In his view, problems are not being addressed with the seriousness they deserve. The combination of sensitive systems and a rushed or careless approach has created a situation where major failures become increasingly likely. The S-36 explosion is a prime example of this. A single flaw in one component cascaded into a full system failure, costing SpaceX a critical prototype and delaying the program's timeline. And while COPV is the current focus, it is only one of the many systems within Starship that require close attention. Issues with engines, flaps, tanks, and plumbing have all emerged at different stages in recent tests. These revelations raise broader questions about the overall workforce culture and management structure at Starbase. While Musk and Shotwell continue to lead SpaceX at the highest level, their direct involvement in Starbase operations appears to have decreased over time. Some suggest that their more frequent presence could help reestablish higher standards and restore stronger oversight to the team working on Starship. Before anything else, SpaceX must now turn its attention to the aftermath at the Massey Test Site. Damage must be assessed and repaired, and new testing systems may need to be constructed to move forward. But more importantly, the internal practices that contributed to this failure must be thoroughly reviewed and improved. Sensitive systems like COPV need clear protocols, better installation practices, and rigorous checks. Broader systems should also be audited to prevent recurring issues. Lessons must be learned not only from the explosion of Ship 36, but also from the earlier problems seen in Flights 8, 9, and other recent test flights. If handled well, this could be a turning point. While the explosion was undoubtedly a major setback, it could also serve as a much-needed wake-up call. SpaceX now has the opportunity to reassess, regroup, and come back stronger. With better systems, improved oversight, and renewed attention to detail, the company can still achieve the goals of reusability, orbital refueling, lunar missions, and eventually, Mars colonization. What do you think of these newly revealed causes behind the Ship 36 failure and the broader issues facing Starship? Is this the time for Musk and SpaceX to refocus and raise the bar across the board? If you agree, comment "Let's do it" down below. And as always, like the video and subscribe to our channel to continue following the incredible journey of SpaceX. Now, let us move on to the latest update on ULA's Atlas V mission. After facing a series of delays due to an earlier engine-related issue, Atlas V mission tasked with deploying Amazon's Kuiper satellites has finally taken flight. This significant launch occurred at 6:54 a.m. Eastern on June 23rd, successfully sending Amazon's second batch of Kuiper satellites into low Earth orbit. The mission proceeded smoothly through all critical flight phases. Notably, the main engine cutoff went off without a hitch, and ULA later confirmed that all 27 Kuiper satellites were successfully deployed into their designated orbit. With this addition, Amazon's Project Kuiper constellation now totals 54 satellites. The first deployment took place on the 28th of April, marking the official start of what is expected to be an ambitious rollout. Project Kuiper is Amazon's answer to SpaceX's Starlink, and the Atlas V plays a key role in its early phase. According to ULA, the Kuiper payloads are the heaviest ever carried by Atlas V at 34,000 pounds or 15,400 kilos. The satellites ride into space attached to a special dispensing tower and release at predetermined intervals, representing the most separation events ever performed in a single Atlas launch. However, these two initial launches are just the tip of the iceberg. Project Kuiper aims to build a broadband internet constellation that will eventually include more than 3,200 satellites. To achieve this, Amazon has secured launch agreements for approximately 80 additional missions over the next several years. The company is aiming to begin delivering internet service to select customers before the end of this year. In terms of launch providers, ULA will remain a central player. Amazon has already booked 8 Atlas V launches and 38 rides on ULA's next-generation Vulcan Centaur rocket. Additionally, Project Kuiper satellites will be sent to orbit aboard Blue Origin's New Glenn and Arianespace's Ariane 6 rockets. As Amazon explained, those agreements comprise the largest commercial procurement of launch capacity in history and support thousands of suppliers and highly skilled jobs across the US and Europe. Yet this ambitious multi-rocket strategy is beginning to show signs of strain. All three of Amazon's contracted launch providers are facing difficulties. The Vulcan Centaur, despite being positioned as the successor to the Atlas V, has only flown twice since the beginning of 2025. Its most recent flight encountered problems with one of its solid rocket boosters, raising concerns about its readiness for regular service. Meanwhile, the Atlas V, although still highly reliable, is now approaching retirement. Only 2 more Atlas V missions are scheduled for Kuiper launches. This leaves a shrinking window of availability for one of Amazon's most trusted launch platforms. Blue Origin's New Glenn rocket has also seen limited activity. Its first mission flew in January, but failed to recover the booster, a setback for a rocket designed with reusability in mind. Since then, there has been little visible progress toward its second flight. Similarly, Arianespace's Ariane 6 has only flown twice and has also faced issues during its second mission. This situation puts Amazon in a challenging position. While it has made historic commitments to secure launch capacity, the reliability and flight cadence of its launch partners have not kept pace with the ambitious timeline for Project Kuiper. As a result, the program risks falling behind Starlink, which already boasts over 7,600 operational satellites and active service around the world. Moving forward, it will be critical for all parties involved in Project Kuiper to make improvements. Launch providers must increase their flight cadence and reliability if Amazon hopes to stay in the race. The remaining Atlas V launches will play a crucial role in keeping that project on track, but long-term success will depend on the rapid maturation of Vulcan, New Glenn, and Ariane 6. So let us keep a close eye on how Amazon and its launch partners respond in the aftermath of this mission. Will they overcome these growing pains and accelerate Project Kuiper's deployment? Only time will tell. And now we shift to China, where the Zhuque-3 rocket is quickly emerging as the centerpiece of the country's push for reusable launch technology. Built by private firm Landspace, the Zhuque-3 builds on the Methalox foundation of its predecessor, the Zhuque-2, but introduces major upgrades aimed at reusability, following the path forged by SpaceX's Falcon 9 and Starship. At midnight Eastern, June 20th, a major milestone was achieved. Landspace successfully conducted a static fire of the Zhuque-3 booster at the Jiuquan Satellite Launch Center. All 9 Tianque-12A engines ignited in sequence, burned for 45 seconds, and shut down as planned. With 7,542 kilonewtons of thrust, the test confirmed the vehicle's heavy lift potential and readiness for its first orbital flight. The test mirrored a full launch cycle, which involves pressurization, multi-engine ignition, gimbal control, steady burn, and shutdown, using the same stage intended for flight. Landspace hailed it as a key step toward making China's reusable rocket ambitions a reality. The inaugural flight, set for the third quarter of this year, is expected to carry a prototype of the Halong cargo craft, developed to support the Tiangong space station. Interestingly, new specs put the Zhuque-3 at 66 meters tall, which is 10 meters shorter than earlier figures. This could indicate reduced payload capacity for early flights, but it doesn't diminish its role as a serious challenger in the global launch market. China's efforts with Zhuque-3 reflect a broader strategy to compete with the West, not just through state programs, but now with commercial ventures as well. The race is no longer defined by governments alone. Companies like Landspace are rising fast. With SpaceX facing delays after Ship 36's explosion and ongoing COPV concerns, the pressure to rebound quickly is real. China's progress adds urgency. The next few months will be pivotal. As we watch Zhuque-3 edge closer to orbit, the modern space race continues to intensify, and the next leap could come from either side of the Pacific. COPV. This is quickly becoming a significant keyword when discussing Starship at this stage of its development. Yes, it is the very component responsible for the recent Ship 36 incident, and it is not the first time this part has been brought up during the long and complex journey of Starship's evolution. So why does SpaceX continue to face challenges with this component, and more importantly, what steps might they take to fix it moving forward? Starship is without a doubt one of the most unique and complex rockets in the world. It is made of many intricate parts and systems, all of which must work in perfect coordination. Because of this complexity, maintaining flawless performance across every flight is incredibly difficult. Over time, we have seen different systems run into issues, from engines and flaps to fuel tanks. Most recently, another system has entered the spotlight, the COPV. COPV stands for Composite Overwrapped Pressure Vessel. It is a lightweight, high pressure container typically made of aluminum and wrapped in a carbon fiber composite. Its role is to store gases such as nitrogen or helium, which are used to pressurize different parts of the rocket. On Starship, the COPVs are located inside the payload section or nose cone and help support critical operations like nitrogen purging and engine spin start procedures. Their lightweight design is key to maintaining performance, which is why after Flight 9, several COPVs were seen washed up along the beach. However, despite their advantages, COPVs are quite complex and vulnerable to failure under extreme conditions. On X, Elon Musk explained, preliminary data suggests that a nitrogen COPV in the payload bay failed before its proof pressure. It appears that during the recent test, the internal pressure exceeded the container's limits, causing the COPV to rupture. The resulting force was powerful enough to blow a hole through the windward side of the vehicle and damage key structures, including fuel lines and the forward dome. This allowed fuel to leak out, ignite, and ultimately cause the massive explosion that destroyed Ship 36. What makes the situation even more challenging is that this appears to be an entirely new failure mode. Musk also said if further investigation confirms that this is what happened, it is the first time ever for this design. SpaceX later confirmed in their official update there is no commonality between the COPVs used on Starship and SpaceX's Falcon rockets. That clarification is important, especially considering that Falcon 9 had its own COPV-related issues during the CRS-7 mission in 2015 and the Amos-6 mission in 2016. So the question now is, why has the COPV become a recurring issue in SpaceX's Starship development? To begin with, one of the primary reasons lies in the inherent complexity of COPV design, especially when it comes to composite materials. These vessels are engineered to hold extremely high-pressure gases, and that requires intricate layers of composite wrapping. When manufacturing or handling is not flawless, this complexity can introduce a range of vulnerabilities. For instance, small flaws such as improper liner bonding, uneven fiber application, or imperfections during the winding process can compromise the vessel's structural integrity. In some cases, the composite layers can warp under stress, creating pockets that may trap liquid oxygen or pressurized gas. This situation can become highly volatile and, under the right conditions, may lead to catastrophic failure. The second contributing factor is the significant difference between the COPVs used in Starship and those used in other vehicles, including SpaceX's Falcon 9. SpaceX and Musk have repeatedly emphasized that Starship's systems are unique. Given that Starship is the largest and most powerful rocket ever built, the pressure and thermal loads are vastly different from those of Falcon 9. Starship must handle greater engine thrust, larger propellant volumes, and stronger structural vibrations, which create harsher environments for all components, especially COPVs. Another major challenge stems from Starship's use of cryogenic fuels. Unlike Falcon 9, which uses a combination of liquid oxygen and kerosene, or RP-1, Starship uses both liquid oxygen and liquid methane, both of which must be kept at extremely low temperatures. This further stresses the composite materials of COPVs, increasing the likelihood of cold-induced brittleness, delamination, or cracking, all of which could lead to failure under pressure. More critically, Starship is designed for full reusability and long-duration missions, such as in-space refueling, lunar landings, and even Mars colonization. That means every component, including the COPVs, must be capable of enduring multiple cycles of pressure, temperature variation, and physical stress. This demand for durability and reusability introduces a new layer of engineering challenges that are very different from those faced with Falcon 9. Elon Musk has even pointed out that the recent incident on Ship 36 is the first time a failure has occurred with this specific COPV design. This makes it clear that although Falcon 9 experienced two major COPV related issues in 2015 and 2016, the knowledge from those events is not directly transferable to Starship. Starship's size, mission objectives, and operational environment make it a different kind of vehicle altogether. Therefore, new solutions and testing regimes are needed. Beyond the technical pressure, there is also significant time pressure. SpaceX's rapid development approach means that Starship is being built and tested in fast cycles, often with limited time between design, construction, and launch attempts. SpaceX accepts that failure is part of the process and uses data from each test to improve future designs. However, this fast pace can also mean that problems emerge before previous issues are fully understood or resolved. In 2025 alone, Starship has already encountered multiple challenges, including harmonic vibrations, unexpected propellant mixing, loss of vehicle control during flight, and now the COPV failure. While this iterative development method can produce results faster, it also exposes the system to a higher risk of unexpected failures. Each flight is intended to build on lessons from the last, but with the pace accelerating, the risk of skipping over important insights also increases. Moreover, Starship is under additional pressure to achieve extremely ambitious goals. It is not just another rocket, it is the backbone of future missions involving two-stage landings, in-orbit refueling, and participation in NASA's Artemis program and Mars colonization plans. These goals force aggressive timelines and sometimes lead to shortcuts in testing or refinement. The need for fast progress can mean some parts like COPVs are not stress tested under the full range of conditions they will encounter during flight. Another contributing factor is the gap between test conditions and actual flight conditions. Some aerospace experts have suggested that Starship's integrated testing process may be insufficient to identify certain failure points. Since components like COPVs may pass bench testing but fail under full stack, cryogenic, or vibration-loaded conditions, issues might go undetected until they cause major incidents. A more isolated and rigorous testing campaign could possibly have caught the COPV flaw that doomed S-36. It is also important to remember that Starship is still a developmental vehicle. NASA does not yet have the same oversight over its COPV systems as it does for Falcon 9 missions. This means that SpaceX largely manages Starship's component testing and quality control internally. Given that, some theorize that the COPVs on recent prototypes may not have been installed or secured correctly, increasing the risk of mechanical failure during operations. Furthermore, locating the COPVs in the nose cone, near pressurized fuel lines, only adds to the risk. If one fails, it could trigger a chain reaction affecting multiple systems at once. There may be even more underlying factors yet to be revealed. If you have any thoughts or additional ideas on why Starship's COPV system continues to be a challenge, feel free to share them in the comments section down below. Then, don't forget to like the video and subscribe to our channel to continue following the ongoing journey of SpaceX's most ambitious project. Now, once the root causes of the incident are identified, the next crucial step will be determining potential solutions and implementing the necessary corrective actions. The first and perhaps most significant solution is to thoroughly investigate and possibly redesign the COPV system. This will depend heavily on the findings of the ongoing investigation. If a fundamental flaw is discovered, SpaceX may need to completely overhaul the current COPV design. This could involve reinforcing the outer casing, improving structural integrity, or even adjusting the internal layout. Special attention will need to be given to the liner joints, which might be upgraded to ensure they can handle repeated stress without compromising durability or reliability. The second step involves enhancing the testing process itself. SpaceX will likely need to expand its test protocols, incorporating both isolated and integrated evaluations of the COPV system. Testing standards should be increased to push the limits of pressure and thermal conditions in order to detect vulnerabilities early. Alongside this, quality control procedures must be tightened across every stage of production, from design and manufacturing to installation and system verification. Personnel involved in these stages may also require updated training, which could be implemented during the downtime while the Massey Test Site undergoes cleanup and repair. With S-36 now lost, S-37 is expected to be next in line, and its COPV system will be closely scrutinized while it remains inside Mega Bay 2. Finally, SpaceX may explore alternative technologies to reduce reliance on the COPV system altogether. One option could be to utilize engine-supplied air for certain pressurization tasks, potentially lowering the operational demands placed on the COPVs. However, this would introduce new engineering challenges, including the design and integration of a supporting system, which may add complexity to the overall architecture. It can be said that even a single incident involving one part of Starship is enough to reveal much about the challenges SpaceX still faces. Starship, a rocket widely considered to be the future of the aerospace industry, remains a highly complex and ambitious system. This complexity makes it extremely difficult for even its creators to maintain complete control over every aspect of its development. The recent issue involving the COPV stands out as a powerful example of the broader challenges within the Starship program. This component, while seemingly minor, has emerged as a focal point for both technical analysis and potential design improvements. In the weeks and months ahead, the COPV will likely receive heightened attention as engineers assess failure points and begin implementing more robust solutions. If SpaceX can overcome this setback, it'll position the company for an even stronger return, pushing toward its long-term goals of reaching the moon, Mars, and beyond. So, let us see how SpaceX responds in the days ahead. This has been Kevin with Great SpaceX. Don't forget to like the video and subscribe if you haven't already to stay up to date with yours truly on the latest milestones in SpaceX's journey. Thank you so much for watching, and always remember, curiosity, imagination, and inspiration will follow you so long as you keep looking up.